Alright, section 8.3, wave characteristics or properties. So by the end of today, I'll be able to identify various components of a typical wave. So for those of you who have either completed grade 11 mathematics, you'll seen some of this before in your trigonometry unit. If you have not, that is absolutely okay. We'll cover them now. So we are going to talk about the shape, the size, amplitude, wavelength, phase, and phase shifts. Those are all going to be important words. They're all listed down here, and we'll talk a little bit about them in the near future. We will point out, let's just grab this shape right here. This is what we consider a very traditional wave. Okay, it isn't the only type, it's just a nice perfect kind to work with. If you've done grade 11 math, you know this is the shape of a sine or a cosine curve. There's a whole bunch of other discussion on that, which we'll leave for grade 11 math. But for us, this is going to model our perfect wave. Okay, it's a perfect periodic wave. Now, this is what we would call one wavelength. So we started here in the middle or at the equilibrium point. We went to the farthest top or vertical location, then we went down to the lowest vertical location, then we returned back to where we started. Now, that isn't the only way to draw this wave. It's just the easiest one to see the complete cycle. You could also stop at or start at the high point, go down and finish at the high point. That is also a complete wave or one cycle. And you could do any points in between as long as you get back to where you started. So if you started here, went down, came back up, and finished, that is also a complete wave. It's just more difficult to see. Okay, so we're not rigid in structure in that it has to start in the middle and go back towards the middle. It's just that's generally the easiest to model, the easiest to visualize. So that's the way we tend to draw them. So a couple things that we'll look at, keywords. Amplitude is the height of the wave measured from the equilibrium. Okay, it's not from the high point to the low point, it's from the equilibrium. There's a sort of an invisible line that travels through the middle of the wave that the wave sort of works its way around. Okay, so that's our equal point or equilibrium, and amplitude is the distance from the maximum to that point. It could also be from the minimum to that point. So those are both amplitudes. Okay, wavelength, we just talked about, that is the length. It's usually measured in millimeters, meters, centimeters, those types of things. And it's the length of one complete cycle. Crest and trough. So crest is how we define the high point. Trough is how we define the low point. Okay, so if we look down here at our list of key terms, let's just slide that up a little higher so we can see. So amplitude, we talked about that displacement from the equilibrium point. Waveform, so as I said, this is a sinusoidal or cosine curve. There's lots of different waveforms. You can have squares, triangles, weird shapes. We keep it simple for grade 11, but if you continue on in higher level mathematics, you'll see lots of different shapes, especially electronics, electricity, those types of areas. They model different waves with different shapes. Crest is the high point, trough is the low point. Wavelength, please note this little symbol, it's lambda. Looks like a little tent or something. It is the length for one complete cycle. Okay, and that little symbol doesn't really communicate that super well, so make a note of that. That strange looking little lambda, this is wavelength, and that's the length of one complete cycle. Okay, so now we'll talk about phase and phase shifting. Phase is just your x location, essentially your x coordinate of your wave. So when you talk about a phase shift, you're talking about how it's moved. So if this is the starting location of the original wave and this is the new location, it has been phase shifted to the right a certain amount. Now that could be measured in time, that could be measured in degrees, that could be measured in centimeters. So phase shift has some flexibility depending on what you're working with. For us, it's usually going to be time, but if you do this in math, you could be an angular measurement, radians, degrees, whatever. Okay, so phase is just your x location. Phase shift is how much you're going to move it left or right. In phase is a way of saying that all of your x points line up. That's basically what that's saying. So if I drew another wave here, and I'll change to red so we can see it. If I drew another wave right on top of this blue wave, that wave is in phase. Okay, it's identical. The crests are at the same location, the troughs are at the same location, everything is perfect. Okay, out of phase would mean I would grab this wave and I would drag it over. That's now out of phase. Okay, it doesn't have to be perfectly, opposites or anything. It just has to be slightly off, and that's considered out of phase. Okay, so now if we said something like this, let's make sure I got enough space here. So a phase shift of lambda over 2, or half a wavelength. So if I went back up here and I wanted to move the red graph half a wavelength would look like that. Okay, sorry, that's a quarter wavelength. Half a wavelength would look like that. Okay, so now we see there are crests and troughs that are lining up. They're completely out of phase. And that's one way to talk about this. That reminds me, though, we should go back up here for a second. Whoa. And take a look at, go up, thank you. What quarter wavelength, half wavelength, and those types of things. They're not always easy to see. This is a quarter wavelength. This is half a wavelength. And those ones aren't too bad. But then if we looked at something like this, that's 3/4 of a wavelength. And again, as long as we stick with the ideal shape, it's easy to see. If you start to move that, it becomes a little bit more difficult. Okay, so if you look at that one, that's half a wavelength. Okay, and it doesn't look like it. It's when you don't use that regular sort of natural blue model that we use that starts at the equilibrium point. This is where it can be a little tricky. We could also have something like this. 3/4 of a wavelength. And you can chop this up in a whole bunch of different ways, but just try and keep an open mind and be familiar that that shape of a really ideal wave, periodic wave, you can start at different locations and you can measure to different pieces. Okay, that's really important. Okay, so frequency, period, and speed. So the first word that we want to address is frequency. And this is one of those big words. You need to write it down. You need to know the units. It's one of the fundamental things we have to know when we talk about waves. So frequency is the number of complete cycles over a unit time. Now normally it's over a second, so we normally say cycles per second, and that has a unit called hertz. Okay, so if you had something that was 60 hertz, so 60 hertz would be 60 cycles per second. Okay, the inverse, the inverse is probably the right way of saying that, is period. And period is the complete, or the time for one complete cycle. Okay, so let's go back. Frequency is the number of cycles per unit time, and period is the time for one complete cycle. Okay, so we have a nice little red box down here, which you always know includes an important formula. So frequency is 1 over the period, and period is equal to 1 over frequency. And again, the definition, frequency is cycles per unit time, period is time per unit cycle. Okay, and once you've done a few of these, it starts to become really straightforward. It's not that complicated, so don't panic right now. Okay, so let's have a quick look down here. This is 1 second. So you have 4 complete cycles in 1 second. So if you have 4 crests per second, that means you have a frequency of 4 hertz. Okay? The period for this, and this would be the time for one complete cycle. So if this is 1 second, each one of these has to be 0.25 seconds. So the period is 0.25. Okay, so if you went frequency equals 1 over 0.25, you would get your 4 hertz. And you can do the other one where you do period equals 1 over frequency. Okay, so period equals 1 over frequency, and there's the 0.25. Cool? Didn't fit there, sorry. Okay, so now if you stay in one spot and you watch or waves go by, we can come up with a wave speed. Okay, so if you imagine we have some or some line here, okay, and I'm going to draw a line. There's my wave, and this will be my eye watching. If I see a wave, a complete wave go by, and I know how long it is in terms of its meter length, so maybe it's 2 meters, okay, and I know the period or how long it takes for one cycle to move through there, I can put those two pieces together and I can come up with a wave speed. Okay, so wave speed here, you'll notice it's very similar to our kinematics. We have meters per second, but notice we're using wavelength and we're using period. Okay, so please note that difference. This is wavelength, which is going to act like our distance traveled, and period, which is going to act as our time value. Okay, and in grade 12, we'll take some time to look at something called simple harmonic motion. We probably won't have time this year to look at it. Something like a mass hanging on a spring bouncing up and down. That's what we call simple harmonic motion. It's just a motion that repeats itself at regular intervals. It makes some calculations and things nice and easy to work with, and it just talks a lot of, or it allows us to talk about energy concepts really nicely, as well as frequency and period and those types of things. So we'll do that in grade 12. So let's just wrap this up. Section 8.3, if you could take a look at 1, 3, and 4. And thank you for tuning in.